All right, it's recording. All right, so yeah, so just want to show you around the interface a little bit of STAR. So it, like I said, it's blank when you first open it up. So you want to go to File and then New to create a new simulation. And then I wrote this in the instructions, but if you have a computer that has multiple cores, you can set it up to take advantage of those multiple cores by clicking this option right here, parallel and localhost. So it'll run some of the processes in parallel, taking advantage of parallel processing, and you can set the amount of cores that you want to be allocated to STAR. So I have 8 cores on my processor, and I'm just going to allocate all of them to the simulation. And then you want to make sure that power on demand is selected and your license key is entered here. So, yeah. So then you can click OK. And it will start up a new simulation. And you can see that this kind of a tree sort of pops up on the left. And the thing about STAR, which a lot of people don't like, include myself included, when starting learning STAR, is that like everything is here and it kind of gets confusing, like where you need to go and everything, because there's just so much information just given at you like all at once. But as you get used to it, you'll get more appreciative and you'll be like, oh, that's so awesome that just everything is just in one location. But yeah, that's how I feel right now. So basically, the first step that you want to do is to import your specific geometry that you want to do tests on. So the way to do that is to right-click 3D CAD models, go to New, and then 3D CAD model 1, and then import CAD model. Have I lost anyone yet? I'm just going to assume that everyone is with me. Then make sure to find those files that I sent in the chat. Download that to your computer. And we're first going to open up this internal flow block.x_t. So this is a parasolid file, and you can get this file from exporting a geometry from NX. And I can show you how to do that maybe a little bit later. But yeah, so just click on that and then just click open. And it will bring the geometry into this window here so that you can see it and make edits if need be. So STAR has like its own like CAD software built in to make things a little bit simpler so that you don't have to like keep on going back and forth from like NX or whatever CAD software you're using to make like iterative changes. You can like make them right here inside STAR. And that's what like this 3D CAD model and 3D CAD view are here for. You can make changes that you want to just on this model itself. But for now, we'll just be sticking with this model. Also want to note that this is an internal flow simulation because the flow is going to be going inside here and then exiting here at the outlet. And I'll be doing an external flow simulation a little bit later as well. So now that we have this geometry imported into STAR, we can update the 3D CAD and then close the 3D CAD since we don't really want to do anything else with it right now. And you can see that it closes that 3D CAD window. So now what you want to do is if you want to see the part, you can right-click Scenes go to new scene, geometry scene. And it's not popped up here yet because we haven't actually added it to our parts. So the way STAR-CCM works is that like it splits up like geometries between the 3D CAD model and the parts that you have. So generally, 3D CAD model is where you like want to do all of your edits and such, but the parts are basically like the geometries that you're going to be running the simulation on after you make any changes to the CAD model. So to create a part, what you want to do is right-click 3D CAD model, and then this will basically create a new geometry part based on everything inside that model. And you want to keep everything that's here. Don't really need to change anything. Everything here is good. And now we have our part, which can now be used in our CFD simulation. So sometimes STAR gets a little bit buggy and it won't like show the body unless you like click on it in your geometry scene. So if that happens, usually you can just like delete the geometry scene and then create a new one. And then, yeah, see, now it just popped up. So is there anyone that does not have this on their screen?
I was actually, could you show how you upload it? I was having issues. I got it downloaded, but haven't actually bringing it up in Star.
Okay, yeah, no problem.
So I'm on
So,
load file.
oh, you're on load file. Okay, so no, so
Yeah.
you want to create a new file.
Oh, okay.
Yeah, yeah. So because this is like a simulation file that we're running, and so like the CAD model is just like something that we import into the simulation file, if that makes sense.
Okay, so just create one, title it default, and then import. So, and then how do I bring in that file?
Right, for sure. So you go under this geometry node right here, and
Cool.
then you open up 3D CAD model, or actually you wouldn't be opening up 3D CAD models. There shouldn't be a plus next to it. You would right click 3D CAD models and then click new.
Okay, cool.
All right, nice. So then what you do then, oh, sorry. You right click the 3D CAD model kind of icon, or not icon, but this like, you just right click this at the top here, and then you go to import and then CAD model.
Okay,
and
cool.
then you just select the dot x_t, and we'll be working with this internal flow block first, not the one with vein.
Cool. All right, cool. Thank you. I got it.
Nice. So yeah, so once you get it inside the 3D CAD model, update 3D CAD, close 3D CAD, and then open up this node next to 3D CAD models, and then right click your 3D CAD model, and then click new geometry part. Are we all there, guys? I can't see anyone's face for some reason. I think when you're screen sharing, it just makes it so much more difficult to use Zoom. Can someone just say like if you're not there?
No,
Okay.
you're good. I see you. Sorry.
Okay, cool.
Off, but yeah.
All right. Nice. So yeah, so now we have our part, and we can make a geometry scene to see that part by just like right clicking scenes, new scene, and then geometry scene. And then just geometry, sorry. And then it should pop up, the part should just automatically pop up into your geometry scene. Okay, So from there, now what we want to do is we want to tell STAR where exactly the air is going to go. We want to, right? Otherwise, it's not going to be able to know how to run a simulation. We need to say, okay, so this is going to be the inlet, this is going to be the outlet, or if we were doing an external flow simulation, what we would be doing is we'd be creating a virtual wind tunnel, which would just be a block, just like a rectangular prism, and we would set one side to be the inlet and correspondingly the other side to be the outlet, and the other sides obviously would just be the walls. So in this case, since we're doing an internal flow simulation, we just want this small location to be the inlet and this small location, this larger location to be the outlet. So the way that we want to specify that STAR-CCM is to first create like a surface to cover up both of these holes on either side. So the way to do that is to make sure that you're in this geometry node right here, and then right-click operations, new, surface preparation, and then fill holes. So then from there, we want to select our input parts. So that'll just be the entire body. And then for part surfaces, oh, sorry, I skipped a step. Sorry about that. I skipped a step. So the way that we want to specify what are the inlet and outlet surfaces first, what we want to do is to open up the node next to body 1, and then open up this surfaces node, right click default, and then split by patch. So here it brings up like this kind of color coded thing, which color codes like each surface essentially. And then we can basically split up this entire surface. Right now, STAR sees this as like one surface. We can specify, okay, we want this surface to be the inlet. So what you would do is you just click on that surface. It should be highlighted purple, and then we can rename it to inlet, and then click create down here, and then it'll hide that surface, which means that it was created successfully. And then correspondingly go to the back, highlight that surface. Again, it'll show up as like purple or pink, whatever. And then we will name that as our outlet. And then we will click create. So now we have the walls of the this geometry that we have, and we have the inlet and the outlet. So now we want to go to where I was going before, right-click operations, go to new, and then surface preparation, fill holes. And then for input parts, we select body 1. For end surfaces, we will select inlet and outlet because those are our two ends. And then for end curves, we'll just select default. And you can click this execute upon creation, and then click OK. So now we have our fill holes part, which now created these two surfaces on either side to fill this geometry or to create these surfaces. Yeah, so now we have those two holes. Now what we want to do is to extract the internal volume from this. So the reason why we want to extract the internal volume is so that we will assign that as basically like our air for STAR-CCM. So the way to do that is to right click operations, go to new, surface preparation again, and then now to extract volume. So what we want to do here is to select both of these, body one and fill holes, and then STAR-CCM will basically just extract that inside volume. And then again, we can just click this execute upon creation. Okay. And now we can see, now we can see our internal volume. So this is where all of our air goes. Is there anyone that is lost, missed a step or anything? Or are we all on the same page?
I think when I selected the fill holes, the three options, I think I might have put them in wrong, or if the
Okay.
surfaces I exploited are wrong. I'm trying to see. Did edit? I labeled the two sides. Actually, I think it's when you labeled them inlet outlet.
Okay.
That I did it.
All right. So you right clicked the default surface and then you split by patch. And
The split by patch is probably it. Yep.
okay.
All right.
And then
And which one did you hit? The just what is it? Sorry, I need to look
yeah,
back
no
at
problem.
yours.
So when you click on split by patch, it doesn't show here since I already did it, but you can click like this, so this surface that was right here, which was solid, and then once you've clicked on it, it should highlight that that like part number or that part patch over here, and then you can name it whatever you want, and then click create. So that would be inlet, and then the other side, you would do the same thing. You just click that. It should be highlighted here, and then you would name that outlet, and then same create.
Okay, cool. I think I got it. And now
Awesome.
it's okay. Now
So
the
now,
extract volume I did,
okay.
or yeah, okay. Let me see. The only thing
Do
is
you want
mine's
to?
not extracting the inside.
Okay. Do you want to just share your screen?
Yeah, I can do that real quick.
That might be easier.
And
Okay.
and I don't know if these exclamation points are
Okay. So yeah. So that
bad.
just means like they haven't been executed. So you can right click operations,
Mm-hmm.
and then
Oh,
and then just execute all. Yeah. Either way works.
okay. Let's
And
see. Hmm. See if I can edit this.
input parts, body one, fill holes. Yeah, that's right. I wonder why it's still showing like that color coded.
We're supposed to hit both of these, right, for end surfaces?
Yeah, that's right.
And then end curves is just default?
Yeah, that's right.
Yeah, I don't know.
Huh. It might just be like the geometry scene is acting up. Like you saw earlier, it just wasn't even showing up for mine. You had to like close it and then open it again.
Oh,
So
yeah. All right, well, I will try
or you don't have to close the entire simulation. You can just close here. Let me
the
annotate.
star 3 or this
Close
closes window. Oh,
just
here.
close. Yeah, just close there, and then oh, you know what? I think you're still on split by patch, so you need to click close. You just click close right here.
Wait, oh.
There it is. Yeah,
Oh,
now it
okay.
looks good.
Oh,
So
sweet.
now if you click on this just one time,
Oh,
yeah, there, sweet. So yeah, so your
perfect.
volume is there.
Cool. All right. Appreciate it.
For sure. All right. So, okay, let me just. So yeah, so now we have our extracted volume. So from there, what we want to do is assign our parts to regions. So this will basically allow us to specify boundary conditions. So by that, all I mean really is to say this side is the inlet and correspondingly a velocity inlet. Velocity inlet would just mean that air is coming in at a constant rate. Or in our case, we're going to set it up as a stagnation inlet, which essentially means that there's just a large, it acts as though there's a large mass of air, just like ready to go through it, ready to go through the inlet. And the way that we get it to come through that inlet is to set a negative pressure boundary on the outlet side to sort of like suck that air in from the stagnation inlet. So the way that we want to set our regions is to right click extract volume and assign parts to regions. And what we want to do here, typically we would want to create one region for all the parts that we have. We only have one part right now. There are specific scenarios where you want to create like a region for each specific part, and I might get into that a little bit later. But for now, just want to create one region for all parts and then create a boundary for each part's surface. So remember earlier when we split by patch, we set it up as an inlet, outlet, and the default to be just the walls. Now it's going to go ahead and create a boundary for each part surface, and now we can specify, oh, this is going to be velocity inlet, stagnation inlet, or this is going to be a pressure outlet, or whatever it may be. And then you can just leave this as is, and same with the other things. And then you just click apply, and then close. I'm just gonna close some of these nodes here because it can get a little bit cluttered. So now we have this regions like node right here, and we can open that up and we can see our region. This is our entire region. This is where all the air is going. This makes sense. Now we can open up more. We can see our boundaries. There's the walls. We can see through it. That makes sense. We see our inlet. That makes sense. We see our outlet, and that makes sense. Now, we can set up what we want these to be. So right now, all of these are set up as walls. You can see down here in the properties tab, or properties, like whatever window, whatever that's called. They're all set up as walls. If you don't see this properties thing right here, what you can do is go to Windows and then click Properties, and it will show back up. Sometimes you might accidentally close it, and then it never really pops back up till you open that again. Okay, so now we can set this up as a stagnation inlet, and set up the outlet as a pressure outlet. And right now you can see that we aren't able to specify any values right now. We can't say, okay, we want the pressure outlet to have a negative pressure of 1,000 pascals, which is what we'll be doing, negative 1,000 pascals. And that's not showing up. We're not able to add that value. And the reason for that is we haven't set up our physics conditions. So each simulation is going to have a different set of physics conditions necessary for it. Specifically for internal flow, I'll go through this as we set them up. So the way to set up your physics conditions is you right-click Continua right here. Then you go to New, and then you go to Physics Continuum. So now you can select the physics models that you want to be run in your simulation. And the way to do that is to right-click physics and then select models. So here you can see a bunch of stuff. And it might not make sense to you at the moment, but we will get there eventually. But yeah, so right now, this is a three-dimensional. Can you guys see this window, by the way? Just checking. Like this physics 1 model selection window that I have open.
Yeah, we can.
Okay, awesome. So yeah, so this is a three-dimensional simulation. We could actually run this as a two-dimensional simulation because there aren't really any changes in the geometry in the Z direction. I mean, in the X direction, I mean. There aren't really any changes in the geometry. So we could really run this as a 2D simulation. But for this simulation, I want to measure the mass flow through the outlet of the duct or whatever this is. I just made this in NX in like 30 minutes. It's just a random thing that I made. But yeah, so we want to find the mass flow through the outlet. So the only way to really do that is to have a three-dimensional simulation. So the material that we're going to be using is gas. We'll just be using air. Air is the default that's like automatically selected. You could select other types of gases and I mean other types of liquids. There's a whole bunch of things that you can do with STAR-CCM, but we'll be using air. And then here comes flow. So coupled flow versus segregated flow. So generally speaking, in simulations that have air speeds that are less than like Mach 1, we can use segregated flow. Sorry, I misspoke. Less than Mach 5, we can use segregated flow. But coupled flow works really well with hypersonic flows, which is flows that are greater than Mach 5. So we won't really be using that or having flow going past Mach 5 in the simulation, so we can use the segregated flow model. The next thing that we want to select is our equation of state. So this is also dependent upon what flow characteristics that we're expecting in our simulation. Generally for external flow simulations that we do on the full car and on the different aerodynamic components of the car, we'll use constant density. The reason for this is that air is pretty much incompressible below Mach 0.3. And Mach 1 is 343 meters per second. Mach 0.3 is like, what is that? Like 100, around 100 meters per second. So our car, just to give you some reference, 35 miles per hour is about 15.64 meters per second. So obviously that's like way below Mach 1, Mach or 100 meters per second. So we usually deal with constant density there. If we're going into like an internal flow simulation, for example, maybe the intake, where flow does reach Mach 1 and maybe even a little bit over Mach 1, we can't assume constant density anymore because the flow is above Mach 0.3, and we then have to select ideal gas. Now, the only time we use real gas model is when we have flows above Mach 5, so hypersonic speeds, which probably won't be dealing with at all in any of our simulations that we'll be running for the USC racing team. But yeah, I mean that's there if need be. And the difference between ideal gas and real gas is that in a real gas model, it'll look at the intermolecular forces because when you're going at such a high speed of like Mach 5 hypersonic, intermolecular forces become very significant in our calculations. So in our case right now, we'll be dealing, I think when I ran it, we saw, if I remember correctly, it was around like 50 meters per second. So we can use constant density. Then for time, some of the models here are unsteady and steady. Basically what this means is, for example, if you're running a simulation on a sphere, the airflow behind the sphere, the wake of the airflow, isn't constant. Like it varies with time. So basically, if we're having a simulation where the airflow is going to vary with time, we'll want to select an unsteady simulation. But in our case, we can just select steady since we're expecting it to converge to a particular result. Finally, we usually want to select turbulent in our models. I won't go too much into this, but basically the way to determine this is to calculate your Reynolds number. But yeah, I won't go too much into this, but yeah, we'll just select the turbulent model for now. And then here are the turbulence specific models. So there's 4 that are here. And again, as you can expect, they depend on our flow characteristics. So in our case, we're dealing with internal flow, and the default, just regular model that we would be selecting is this Spalart-Allmaras. Don't know how to say that. But if we're dealing with an external flow simulation, again, like on the aerodynamic components of our car, we would select the K omega turbulent model. And that is all of our physics models set up here. And these are all optional, which are not necessary. Yep. Then you can click close. All of our physics models are set.
Ron, could you go over just time when you use which specific case?
For the turbulent models?
Yeah.
Right. So here, I'll just go back here. So yeah, so by the way, these are all run by the Reynolds average Navier-Stokes equations. And you'll learn about Navier-Stokes in your fluid dynamics class. I haven't even taken fluid dynamics yet, but so I don't really know too much about the Navier-Stokes equations, but yeah. One other thing to note though is that, you know what, I won't get into that. But yeah, so Spalart-Allmaras is for internal flow, and then K omega is for external flow.
Okay, great, thanks.
Yeah. So, another thing to note is that you can set up your specific initial conditions in the simulation. The reason why you'd want to do that is to basically make the simulation run faster. So what these initial conditions mean is that all of these values will be applicable to all of the fluid at the initialized points in time, at that like t equals 0. And you can set like the velocity to go in a certain direction for all of the flow, all of the fluid in your region at the initialized point, because that just makes like the simulation run faster, so that basically it doesn't have to propagate all the way from like the inlet. If you're using like a velocity inlet, it doesn't have to propagate the solution all the way from there all the way to your outlet. It can just run a little bit faster when it's set up that way. But we won't be doing that since this is a really, really small, like I'm pretty sure it's like 15 millimeters, if I remember correctly, something like that. Yeah, so like 20 millimeters. Yeah, so it's like super, super small. So we don't have to really do that. So now we can go back to our regions, and you'll notice on the boundary, we can see that nodes have popped up, and we can specify our physics conditions and physics values. So now we can set up like our inlet. We won't really be setting up any values here, but just to give you an idea, if this was a velocity inlet, we would set up the magnitude of air that is going to be flowing through all of that space at once. And that's how you would do it in like a wind tunnel simulation. You would set up, you would say like the wind tunnel inlet, the velocity would be going at 15.64 meters per second. That's about 35 miles per hour. And that's what you would do. So let me change this back to stagnation inlet. So what we will change is the outlet condition. We will change the pressure. And just note down here, this is gauge pressure. Sure you guys know the difference between absolute and gauge, but just to give you a reference again, gauge pressure is 0 at sea level, because yeah, I mean gauge pressure is 0 at sea level, but the absolute pressure would be 101 kilopascals. So we will set this up as negative 1,000 pascals. So basically, if this were absolute pressure, it'd be 100 kilopascals here, and then at the inlet would be 101 kilopascals. So where does the air want to flow? It wants to flow to the right, right? To just meet that pressure differential. Okay, so does everyone have this set up? These boundary conditions set up? Or does anyone not have these boundary conditions set up and needs help? Okay, very nice. So we have our region set up. So we are not done yet. We cannot click run. There is one more very, very crucial step that we have to do, and that's to set up our mesh. So what is a mesh, you ask? What a mesh is basically, we can't model every single molecule of air inside our region, right? So what we do instead is we set up a mesh to specify, okay, the values in this cell or this parcel of air are going to be identical throughout. So we don't need to basically model all of the physics that go between inside that cell, inside that parcel of air. We only need to model the physics interactions between a cell and the next cell. And to get an idea of what I mean by that, we will make a mesh. So the way to make a mesh is that you go all the way to the top to our geometry and open up the node next to that. And we will be going back to operations, and then right-click operations, go to new, and then go to mesh, and then go to automated mesh. And then here, we want to select where the mesh is to be done upon. And in our case, we want it to be done on the extracted volume. Yeah. And so the next step is to select our meshers. Usually, the rule of thumb here is that you want to use the trimmed cell mesher on external flow applications, and you want to use the polyhedral or tetrahedral mesh on internal flow applications. So since this is an internal flow sim, we'll use the polyhedral mesher. We will use the surface remesher. We'll select automatic surface repair. And then one more important thing is this prism layer mesher. I will get into what that means later. So now what we want to do is select our controls for this specific mesh. What are the values that we want this mesh to have? How big do we want those cells to be that I was talking about earlier? Do we want them to be 1 meter? Probably not, right? Considering that this is like on the scale of millimeters. If we had base size of 1 meter, I mean, let's see what happens. I don't even know what star will do. It will just disappear. Okay. All right. So yeah, we don't want that. We want a base size that is much smaller. Now I can't even see the geometry. I shouldn't have done that. Let me okay, there it is. Okay. Oh, you know what? Yeah, it did mesh. This is our mesh. It's just one cell. If it wants to do the Navier-Stokes equations, it'll have to do it on one cell. Okay, but yeah, so we'll have to select what our base size should be. So the way that we want to select base size is honestly, and I'm not making this up, this is just like a guess and check game, meshing. You want to see, obviously, the more finer your mesh is, the higher fidelity answer that you're going to get from your simulation, because you'll be modeling interactions on a smaller scale, which models real life more. But the cost of that is that your sim is going to run a lot slower, right? There's a computational cost to that. So you want to like basically trial and error it. When I was first working with STAR, I had made some meshes which were too fine and crashed my computer a couple of times because I did not realize that you shouldn't make a mesh 1 millimeter in size when you have a region that is 10 meters large. But yeah, so basically you just want to like get a feel for what the mesh size should be. And the way to do that is to just click on this ruler icon and then kind of think, okay, yeah, that's probably like a good cell size that we want to do, that we want to use. Like, yeah, they'll probably model our conditions as we wanted them to be. If our result isn't converging, if we're not getting a proper result that we're expecting, maybe we need to use a finer mesh. But I think this is probably a good starting point. So we can use 0.005 meters as our base size for the cell. Then there's this next thing, target surface size. So basically, that just means like, I mean, it's pretty self-explanatory. The mesh software will want to target this size, but if it feels like it doesn't need to be as small, then it'll just default back to the base size. So usually this target surface size will be smaller than our base size. But we can just keep it as 100% for now. And then minimum surface size. So again, pretty self-explanatory. It'll go to it'll make the mesh go to as this fine if it determines that that's necessary. Surface curvature, basically, what that means is if you have like a round object, the higher surface curvature that you have, the more finer basically that circle or that round object is going to be modeled. I mean, you can just think about it. If you have 3 points in your circle, it's a triangle. It's not a circle. But yeah, if you have like 36 points, it's probably going to be like properly round. That's a fine default value. We don't even have any round surfaces, or actually, that is wrong. We do have this spline geometry here, but we'll just leave 36 points per circle as is. And the next thing that we want to do is select the number of prism layers. So I wanted to talk about this a little bit. Let me reshare my screen. I have a picture I want to show you guys. I guess I must have, yeah, here, no slip condition. Okay, so yeah, this is a good picture that shows it well. Can you guys all see this picture?
Yeah. Yeah.
All right, very nice. So basically, what this no slip condition means is that at a boundary, at a physical surface, the velocity of air is going to be.
We can see it now.
Okay, cool. Wait, you can't see it now?
No, we can't. It looks like a black line.
Huh. You know what? Let me stop share. And I'll just share my whole screen. How's that?
Yeah, you can see now.
Awesome. Okay. So basically what the no slip condition means is at a surface, there is zero velocity. If you think about your car, or maybe not your car, but your parents' car or whatever, if it gets dusty and you drive like 60 miles an hour on the highway, why does the dust not fall off? It's because of this no slip condition, because the velocity of air at the surface is actually zero. There's air is not moving at the surface. And the reason for that is because of friction, right? So if air were to move at the surface, there would be an immense amount of friction between the air molecules and the molecules on the surface of your car. And that the air doesn't want to do that. Why it doesn't want to spend any extra effort than it needs to. So obviously, not obviously, but yeah, so that's where this no slip condition comes from, basically. But as you go higher and higher, there's this boundary layer which is created, which is like modeled by this sort of like arrows here, which show that slowly as you move higher and higher up, the velocity of air gets faster and faster until at a certain point where it reaches the velocity of your free stream of whatever the constant velocity of air is in your surroundings. If you're going down the highway at 60 miles an hour, there will be a point at which, and this is the top of the boundary layer, the air will be going the same speed as that free stream situation. So the distance between that height and your surface is our boundary layer thickness. And what this prism layers try to do is to model that, basically. It wants to model that boundary layer. The way that it does that is you'll see yeah, it's probably better if I show it to you after it's run. But for now, let's just select 7 layers, 7 prism layers. We'll leave prism layer stretching as is, and the total thickness, maybe change it 10% of our base size. And we will run our mesh now. So the way to do that is to right click this automated mesh and then click execute. And now it's been run. You can see like automatically like it became a lot smoother than it was before. And the way to see your mesh is to there's a couple of there's two main options that you can use. In your geometry scene, you can click this button here, which says show all meshes, and then it'll show like these cells that we have. Or another way is to right click scenes, go to new scene, and then mesh scene. So sometimes, I mean, usually you'll want to create a new scene because you don't want to clutter up your geometry scene with anything. But yeah, so what I was talking about earlier about the boundary layer. So we can see here that that the prism layers are super fine close to the surface and gradually get larger as you go out. And this is what we want because of that boundary layer condition, where you can see like the slope of that like relative velocity kind of curve is pretty high. Or when I say slope, I mean in terms of x distance changing as a function of y. So like there's a pretty like the velocity changes quicker as you move higher at the bottom here than it does at the top here, right? So that's why it's modeled like this. It wants to save as much computational resources as possible. That's why it's super fine at the bottom, because the velocity can change quickly between the prism layers, whereas higher up, they're probably not going to change quicker. So I think that is a sufficient explanation. Next, what we can do is we can say that, okay, yeah, this is probably a fine mesh, or I mean a good enough mesh. Yeah, I don't think there's anything else to do here. Let me just think if I'm forgetting anything. I don't believe so. Does everyone see this on my as it is on my screen, or does anyone not see it? See this on like on their STAR-CCM? Okay. Like where do you think? You're a little quiet.
Oh, am I? Can you hear me now?
Yeah, I can hear. I'm just turning up the volume. Okay, where did you get lost?
The default controls.
Okay, yeah. So, do you see this automated mesh thing here?
Yeah.
And then when you open up this node next to default controls, you can see all of this. Okay. So on base size, we select 0.005 meters. On target surface size, we leave as is. On minimum surface size, leave as is. Surface curvature, leave as is. And then yeah, I think number of prism layers, I selected 7. And then prism layer stretching, leave as is. And then prism layer total thickness, 10%. And then everything else was leave as is. But yeah. Yep. Okay. So do you have that?
No, mine shows triangles.
Okay. You might have if you can you open up measures and then you probably selected tetrahedral.
No, mine shows the same as yours.
What? Can you share your screen?
Yeah.
Wait, why is it polyhedral for internal sims? That is what STAR-CCM recommends. I honestly don't know the exact reason for that. I would assume though that the trim cell measure that we use in our external flow applications are just like basically squares and rectangles. So I would assume that basically that's a lower fidelity. So because we have such a large space when we're doing an external flow simulation, it's like that, Kieran.
Okay.
Okay, so this is because you did not execute your mesh yet, I think. So if you go up, if you scroll up here, yeah, if you right click automated mesh and then click execute. So now it disappears like Star loves to do. So what you can do is you can delete this geometry scene and then create a new one. And now click that button up there. Yeah, there it is. So the reason why I was showing triangles is like that's basically how Parasolid file works. It just it makes those lines and it stores the file as like those lines. Yeah.
Thank you.
For sure. Okay, back to our simulation. So now we have this mesh setup, and this should be everything. I am pretty confident that this is everything, and if not, well, yeah, I'm pretty sure this is everything. I think yeah. So now we can just run our simulation, but before we do that, we want to watch what's going on when we're running our simulation. We want to we want to see like, okay, is there like flow separation here? What is going on with the airflow? We don't want to just like let our sim run for a long time and then see what's going on later. There are some situations where you would want that if like it takes up too much computational resources, but in our situation, doesn't matter since it's such a small simulation anyways. So the way we do that is we want to set up a plane which is normal to the x-axis, and we'll split this geometry in half. We'll split the geometry in half so we can see what the flow is doing halfway through. So the way to make that plane is to right-click the right parts, new part, section, then we go to plane, and now its default normal is to Z. That's what this like 1 means. It's normal to Z, so we can change, or actually, we can change it to be normal to Y, I mean to X, sorry, and make that 1 and make Z 0. So that now we can see this is the plane that we want. And you don't have to change anything about the origin. That's fine. Yeah, and this is good. And then what we want to do here is just click create. Actually, yeah, just click create, and then close, and that is it. You can see like there's a line split up there, which is where the where the plane is. And if you want to see it actually, you can just right click this the sides of our like geometry and then click hide. There's our plane. We can see the prism layer, the boundary layer. We can see the mesh in the middle, and yeah. That is good. This is what we want. So now what we want to do is we want to create a vector scene which will show what the flow is doing. So the way that we do that is we right click scenes, go to new scene, and then vector. Nothing shows up except some outlines. So the way to edit that is to, so there's two ways. To do this. You can either open up the node next to scenes, but what I prefer is to like not clutter up this simulation tree. Is now that you have this scene open, you can click on this tab up top. You see there's two tabs, simulation and then scene plot, and it'll automatically basically get the settings for the scene that you currently have open. So if I have like this geometry, you can see like it switches to like the geometry, scene one, switch to the vector scene one, it automatically switches. So what we want to do here is see the flow on that plane. So there are, again, there are two ways to do that. You can, the way I prefer to get the plane over here is to go back to simulation, open up the derived parts node, and that plane section that we created, it should be there, and to just drag it to this window, and then just drop it anywhere in that window, and then you can select displayers. So like basically, where do you want this plane to show up on? What is it pertinent to? If you select outline one, it will just show the plane. It won't plot any data on it. But if we click vector one, it will plot data on it. It will plot our vector distribution onto it. Obviously, after the sim has run for some time, nothing has happened yet, so nothing is showing on our screens. And what I prefer to use for the vector displayer is line integral convolution, and you'll see the difference between the two once we run the simulation. But there are situations where you want glyph, but we'll have line integral convolution set up for now. And I think we are finally done and we can run our simulation. Yeah, I think that's it. Let me just think for a bit more. Yeah, that should be it. So the way that we run our simulation, pretty straightforward. There's this guy up here that says run. And then you just run the simulation. You can click run. And you can see that this thing pops up called residuals. I'll get into that a little bit later. But here is our vector scene. It shows immediately what is going on. Also, by the way, something to note in STAR, if you want to like get a quick view on something, you can make sure to click the scene that you're like in the scene, and then you just click like T for top, S for side. If you click S again, it'll go to the other side. Same with top, it'll go back to the, if you click T again, it'll go to the bottom, and then F for front, and then click F again, and it'll go to the back. So, yeah. So we wanna, this is the front that we wanna see, and yeah, so now we can just let our simulation run for a bit, and you can see like a bunch of things are happening here. Most pertinent or most important thing that is happening here is that there is flow separation. What that means is at this point right here, also just note that like color represents velocity, so blue is stagnant flow, which is not good. But yeah, so at this point here, the flow is detaching from the sides and creating this recirculating region. And you can't see it that well in this line integral convolution setup, but if we go back the scene plot, go to our vector 1, and then go down to properties and select glyph, we can see, well, can't see it that well here because they're so small, but if I change the size of the glyph to maybe 20%, we can see that this is not what we want. We want the flow to come in at this inlet and have a decently uniform distribution going outwards on the outlet. But as we can see here, there is reversed flow. Flow is coming inside from the outlet and recirculating in here due to that flow separation, which is not good. We don't want that. Yeah. One thing which I forgot to add before that we need to set up. Let me just, let's do that right now. Oftentimes when we're running a simulation, we don't just want to like see this and make a decision based off of this. Obviously, there's a lot more than just the visual aspect of the simulation. There are values that we want to gather. For example, we can gather downforce that a wing produces. In this case, we want to measure mass flow through the outlet. So the way that we want to do that is to go to our simulation, set up simulation tree at the left tab there, and we want to create a report. So the way to do that is to right-click Reports, New Report, Flow Energy, and then Mass Flow. You can see that there are a bunch of things here that we can see. The most common things that we would be using in racing are force coefficient, probably mass flow, maybe a moment, maybe even a pressure drop. If we're modeling like a pressure drop over the radiator, we want to obviously maximize the pressure drop over the radiator so that when there's a greater pressure differential, the flow is going to be going as fast as possible through the radiator. So yeah, so in this case, we want to just measure mass flow at the outlet. So we create that report. We can rename it to whatever we want. Let's just say outlet mass flow. Keep the units as kilograms per second, or actually we can change it to grams per second since this is a smaller application. Yeah. So then we want to select where we want to measure the mass flow through. We want to measure it through the outlet. You can measure it through the inlet. In either case, they should be equal. Since we're dealing with incompressible flow, even if we were dealing with compressible flow, mass flow in has to equal mass flow out because conservation of mass. So yeah, you could do it at either, but yeah, we'll just do it at the outlet. Yep. So now it can, now if we run this report, it will tell us what the mass flow is. Tells us we are getting 1 gram per second of air. No, 10 grams. Yeah, 10 grams of air per second through the outlet. Usually what we want to do is create a monitor and plot from that report, since that value will fluctuate throughout the time that you're running the simulation. And you can see that we can clear our solution by going to solution, clear solution, and then just leave history and fields checked. Click OK. And then usually what we want to do is monitor our value that we're looking for, whether it be downforce, mass flow, where is the center of pressure on the car, whatever it might be. We want to monitor and see that result converges to a particular number. Same go with our residuals. And basically, in a nutshell, what residuals measure are, in the simplest terms, I would say how much has the solution changed from the previous iteration, right? So the solution will start at iteration number 1, and it will see how much is the solution changing from the previous iteration. And once that converges to a specific result, we know that the solution isn't changing much. It's staying at a particular value. But yeah, that is that. So now if we run, we can see that residuals are going down, which are good. We can see that this residual has already converged to a particular result. We can see that our other residuals are starting to converge. Yep, pretty much everything has converged now. We have our solution. If we look at our mass flow as well, I'm going to just change this this plot setting. And the way to quickly do that is, again, you have this plot open. You can go to scene plot, click on our left axis. I'm going to set the minimum to 0 and lock that minimum, so it'll make sure to keep that minimum always. And we can see that our mass flow has also converged to 10.1876 grams per second. That is our value that we would note down. That is our value that we would try to optimize, essentially. And the way that we would want to optimize it is to fix this flow separation that's going on, right? So let me change this back to, yeah. So we want to fix this flow separation. So right off the bat, we can come up with a couple of solutions to this. We could create a vein right here, create another vein right here, which basically will direct this airflow. Instead of just going straight down, instead it'll go through this channel. Same with the airflow here. Instead of just going straight down and detaching, it'll be forced to go through this channel. And we could create, we could reduce the amount of flow separation going on over here pretty significantly. So I already went ahead and made a NX model of that. And that is what that second parasol is. it is the internal flow, same geometry, but with a vane. And I won't go through the entire setup of the sim, it's exactly the same, but I want to show you guys like how the iterative design process can work, where we can change certain parameters, add some things, and quickly come up with solutions and validate it within STAR-CCM. So now let me close some of these other tabs open that we have open, and let me open up the geometry scene here so that we can see what's going on. Okay, so this doesn't show it as well. Sorry. Let's look at the CAD model instead. Okay, here this shows it pretty well, I think. Yeah, so I basically added these two like vanes here, which try to direct the airflow a little bit more, so that there's not just immediate flow separation. Again, this was pretty random. I literally just made random spline, a random spline that I thought would look good, and that's what this is. But we can see that when we open up the vector scene here, there's a lot less flow separation that's going on, right? Obviously, there's still a bunch here. We could have made the spline a little bit better. Maybe we can add, maybe we can add 3 vanes instead of 2, which could make the solution a little bit better. But yeah, and if we look at the, let me load the other sim that I had without the vane, and then we can compare it, because I might have accidentally changed some values up when I was going through the tutorial today, but I set this up earlier with identical values between the two to have a good comparison. Give me a second. So let me close this 3D CAD. Also, you can see that the mesh is a little bit finer here. But yeah. Okay, so here is our one vector scene with the vanes, and let me open up the vector scene without the vane, and you can see like there's a pretty stark contrast there, right? Just between those two simple things. And now if I look at mass flow for this, I am getting 9 point, what is this, like 9.7 grams per second versus this is without the vanes, and then with the vane I am getting 10 grams per second. So we can clearly see that there's a quantifiable increase in mass flow between the two. And what is that, like 9.7 to 10? It is 3. It's a 3% increase in mass flow. It's not bad at all, especially for just a random ass spline that I made in just a couple seconds. But yeah, I was thinking that I could make a small little homework assignment and try to see who could maximize like mass flow the most by creating like maybe the best spline geometry or whatnot. And I can upload the exact characteristics that I have with my mesh setup here so that we have like comparable results. But yeah, if you guys want to, I thought that would be a fun little thing to do to try to do that. But yeah, so I can show you how I made this in NX. Yeah, why don't we do that? Does anyone have any questions, by the way, so far?
Well, actually, you were saying that you can actually do some of the adjustments in STAR-CCM, or you have to do it in NX?
Yes, you can do it in STAR-CCM, but the CAD is very, very limited. I tried creating a spline geometry in the STAR-CCM CAD earlier today, and I struggled a lot. I ended up just giving up and doing it in NX because it seemed a lot more simpler.
I'm just curious because I was probably thinking it's probably difficult to make geometry, but probably adjusting the geometry is probably a little easier in there. I don't know.
Yeah, exactly. Yeah, that's the whole point of like having the CAD here. It's not for like making things as much as it is just to like edit small things here and there.
Okay, cool.
But I mean, yeah, theoretically you should be able to create like the spline geometry here in STAR-CCM CAD, but yeah, I struggled a bit with it. So it looks like we don't have enough time to go over the external flow simulation. I guess we'll leave that for another workshop, but I'm gonna go through NX and wait, let me see if I'm connected to, yeah, I'm connected to the VPN. Okay. I'm gonna go through how I created it in NX for those of you that wanna look more into this and try to see if you can maximize mass flow through here. I thought it'd be a good way to get introduced to STAR. But yeah, so
Could you send us the PRT file?
yeah, will do. I will do that. For those of you not familiar with NX, you always want to go as saved, fully load. If you're opening files from drive stream, or actually technically it doesn't really matter if you're doing it on your own PC, like if the file is on your own desktop. But I guess just to be safe, it doesn't really hurt. But yeah, so let's open this PRT file and then I'll just quickly show exactly the steps that went through this. Yeah. So basically, what I did to create those veins, let me remember what I did. I'm pretty sure I just, yeah, okay. So basically what I did was I created a sketch on this plane right here. And then I created a spline that seemed like it would direct the airflow properly. Basically what I did was I just kind of alt tabbed between the vector scene here to kind of like see, okay, so the flow looks clean here. I want to direct it in this direction. So that's what I did. And the way to create a spline geometry, why don't I just backstep and delete this, and then I'll just do it from scratch. Delete, delete, delete. Okay, so yeah, I will send this PRT file to you guys, and then just create a datum plane on this surface here. And then we want it to be at that specific surface. Click OK. There's our datum plane, which we create our sketch on. We can sketch on this datum plane, select where our horizontal reference vector is. Usually what I do is just select the right horizontal direction. Don't really know what's like the correct way of doing this. I haven't taken the AME 308 yet, but that's what I usually do. And then just click OK. And then what you can do from there is create your spline. So the way to do that is to just go up here to spline. And then, like I said earlier, I kind of just eyeballed it. But let's just say, okay, we're going to start our vein here. We're going to end it. Let's end it over here. So now we have this line, and we can create points, add points to this line by just like clicking on it. And then we can move this point to like create our spline geometry however we want it to be. But yeah, so that looks good to me. Then you can just click OK. Don't worry about that. And then I just created a small line, horizontal line, 1 millimeter wide, to just give it some thickness. And then I created another spline, tried to model like as closely as possible to the other one. It wasn't exact, but shouldn't be too big of a deal. But yeah, so there it is. Okay. There's one vein right there. And we just click finish. Now we have our sketch. We can extrude it. I'm going to extrude that sketch. That's the wrong direction. So I can click this right here to reverse it in the other direction. That button right there. Oh, and the distance is 15 millimeters to get it all the way through, because that is the total thickness of this entire object. Yeah, so that's it. So then you just click OK. Wait, what did I do? I did something wrong. Edit. I don't want to subtract. I want to unite. Wait. Yeah, I want to unite. So then it like creates like an extrusion there. And then I think that's kind of weird. Last time I did it, I didn't have to click that unite thing. I did it afterwards. Not sure. Okay, so yeah, so this is one solid body now. So depending on what happens, I guess, if you have this unite option here, you don't have to do anything after. But if it just creates an extrusion that's separate, you want to unite the two together by just like clicking one and then clicking the other, and then just click OK, and then it'll unite the two together. And then that's it. Also, from there, you want to export this as a parasolid. This is the .x_t file that I had sent earlier in the chat. The way to do that is to just go to File, Export, Parasolid, and then you click on the object that you want. You can see that everything is highlighted. This is what we like. And then you can just click OK, and then you can name it whatever you want right there. Click OK. Now you have your parasolid, and we're back to step 1 in STAR, where we import our geometry. One more thing that I want to note is that if you're doing this and you're like iterating through a design, usually, and especially like in this scenario, we're just adding something to this already existing geometry. Or even if you're changing this existing geometry and you're iterating upon it, something really cool in STAR is that you can model re-import so that basically your entire setup is saved, and you can pretty much just remesh, re-execute all of your operations, and then run, which makes it super easy to like iteratively design. And there are these other things called design parameters, which you actually can make it automated with a Java file, a macro, and you can say like iterate through, like, for example, these set angled attacks. And I haven't actually looked much into it. I will, and then I'll cover it in the next lecture that we have. Okay, so we have our exported file. So let's go back to our simulation. I'm going to close these other ones that I had as examples. No, I don't want to save. And no, I don't want to save this one either. Okay, so basically what you want to do here to model re-import, or actually first I should note, you want to save this file as many times as possible when you're setting it up, so that if in case STAR crashes, nothing bad, you won't like lose your actual data or anything like that. So that is a key point to note. One other thing is to note this autosave function, which can basically autosave your simulation after a set amount of iterations. So generally I keep it at 100. All you have to do is click enabled here, set your iteration frequency to whatever you please. I set it as 100, click close. And now every single time it iterates through 100, every single time it goes through 100 iterations, it will autosave your file. So if you're running this overnight, running a simulation overnight, you very much want that. A couple of times I have lost hours and hours of data because I did not have that setting configured. Okay, back to the model re-import. So the way that we do that is to open up our geometry node again, edit our 3D CAD model, click edit, and then we can model re-import here. So the way to do that is to right click this import CAD. Sorry, give me a sec. So we can click this model re-import right here, and then select our new parasolid file. So I'm going to select this internal flow block with vein, and then STAR will pop up this like nifty tool here where you can replace bodies. This becomes especially helpful when you have a large assembly of parts, like we do when we run full car simulations and we want to replace like a specific setup. Let's say that we're iterating upon the duct design, which is like, as I said at the beginning of our shop hours, that is something that we may want to do, update our duct design. So basically what would happen is at the top here, it'll show the old model of the entire car. On the bottom, it'll show the new model or whatever is being imported. and you can basically match the pieces together. And in this case, Star automatically did it for us. I mean, we only really have one piece, so it doesn't really have another option. But you can see like that these parts have already been matched together. You can see like in this top portion, this is our old thing, and then this is our new one. You can see the two veins there in the bottom. So now we can go to match faces, and it looks like Star automatically did this, but very often is the case that you will have to manually go and select all the faces that are to be matched between the two geometries. And then you pretty much just click replace body. That's it. And then you click OK. And now, awesome. Our 3D CAD model is updated. We can update 3D CAD. We can close our 3D CAD model. And we can see that if we open up this node called operations, that there are exclamation marks next to all of them. This means that these operations basically haven't been run on the current geometry that we have. So quick way to do this is to right click operations, execute all, and everything is done. We can open up our geometry scene, and we can see in our mesh that everything is showing up correctly. Our prism layers are showing up here. Everything looks good. This makes sense. Yeah, so it's been set up. So yeah, so that's literally it. You just yeah, you just model reimport, right click operations, execute all. What I would suggest is before you do that, save as a new name, so that basically you don't overwrite your existing simulation. Yeah, but that's pretty much it. Like I can run this now, and oh, actually, whenever you change your geometry, you don't want to keep the solution that has been created before. You want to clear that solution. There are instances where you want to keep your solution, and that's when you're changing your mesh. If you're refining your mesh in a particular area, you're looking at, let's say that, for example, you're looking at some region in our mesh, and we saw like, oh, the boundary layer isn't really defined properly in this location. Let's refine the mesh there. You don't want to waste the computational time that you've spent running the solution before, so you can just basically keep the solution before, and it'll interpolate that solution onto the new mesh that you have. But yeah, but in our case, since we're actually changing the geometry setup, we always want a clear solution like that, and that's it. And then we can just run. And yeah, you can see here, like, wow, the flow separation is reduced a lot from before. And yeah, you can see like the value of mass flow went from like 10 grams per second to about 11 grams per second. And the reason why these values are different from the two sims that I had open earlier is because the mesh might not have been refined as much as possible. This is a pretty big thing in computational fluid dynamics, is called mesh independent studies. Basically, what that means is that our solution currently is dependent on the mesh, right? The solution has changed in our two configurations with the same exact geometry. The solution that we got is different between those two different meshes that we have. So generally what a mesh independent study will do is you'll be refining your mesh more and more till the solution is independent of the mesh, hence mesh independent study. Yeah. Yep. Does anyone have any questions on the content that I've covered so far?
Good right now, I think.
Awesome. All right. So, I did want to go into external flow simulation. I can start it now, but I definitely won't finish. I don't have geometries for you guys for this one because these sims are a lot. External flow sims are generally a lot larger in terms of the computational time needed to run. So I didn't want to do that during this tutorial, but I want to show you guys what an external flow simulation looks like. Okay, I'm gonna choose this one. I'll just show you guys what it looks like, and then in our next tutorial, I can go over how to set it up. But yeah, this is a full car simulation. If I open up the geometry scene, you'll see what I'm talking about. Yeah, this is the rear wing isn't included here because this is a specific simulation to optimize the airflow to the duct. That would just take up extra computational resources that aren't really necessary to model our situation. But all right, yeah. So this is our inlet. This is our inlet to the wind tunnel. This is our outlet. And then these are our walls. And you can see that only half the car is modeled because the car is symmetric. So we can use these things called symmetry planes. Remember before in the other boundary setup that we had, we set them up as walls. So these can be symmetry planes, which basically tell STAR that there is stuff on other. You need to mirror like the result on the other side. This isn't just like half the car isn't just being modeled here, right? So it just tell STAR that this is just like a reflection or just like half of that we have here. But yeah, so yeah, I won't get into this now, but I just wanted to show you guys what that looks like. For those of you guys who haven't seen what a full car sim looks like. In our case, we have two regions, one for the entire subtract and one which is specifically for the radiator. The reason we do that is because the radiator is a porous region that we set up here. Air can flow through it. And yeah. Okay, I think we'll stop there for today. I hope you guys enjoyed that introduction to STAR. Yeah.
Appreciate it, man.
Awesome.
Cool stuff.
Yeah, for sure. I definitely think so as well.
Where's the recording for this gonna be so I can go back when I'm doing this?
Yeah, for sure. I will upload it to Google Drive probably, and I'll send a link in the Arrow chat
Dope. I appreciate that.
for sure. All right. Well,